is the fourth section of chapter 3, further centres of mass, and this section is about rigid bodies in equilibrium. So here are some examples. Got a cylinder being suspended from this point here, and you can see the centre of mass of the cylinder is directly vertically below that point of suspension. Here's an example here, hemisphere being suspended from this point. Again, the centre of mass directly below the point of suspension. In the third example here, we've got a sphere actually being suspended from two different points. In this case, like, the centre of mass isn't going to be directly below one of these, but what we would do is maybe use the tension, call this T1, T2 for example, and then on a question like this we would resolve the forces vertically, maybe even horizontally as well, and also take moments. So there's going to be some trigonometry involved to work out some distances so that we can take moments from any point, but normally a point where we've got an unknown, just to make the working a little bit easier. So centre of mass directly below the point of suspension. Again here, this one, two cables or wires or bits of string suspending this rigid body here, and we resolve forces horizontally, maybe vertically as well, and take moments. Example 15. A uniform solid hemisphere has radius r, so I've got a hemisphere of radius r here. It's suspended by a string attached to a point A, so let's call this A here, on the rim of its base. It's just on the rim of its base here. Find the angle between the axis of the hemisphere and the downward vertical when the hemisphere is in equilibrium. So we're going to have the centre of mass somewhere down here, we'll call that G. This line is going to be directly underneath the point at which it's suspended. And the question says find the angle between the axis of the hemisphere and the downward vertical. Well, this is the downward vertical. The axis of the hemisphere is like its axis of symmetry. So that's going to be this line here. And the angle we want to find is going to be this angle. So I might draw this part of the diagram out like a little bit bigger to help. So just here's an enlarged version of what's going on here. So this is that point of suspension here. Here's the centre of gravity. This is this axis of the hemisphere, and this is the radius here. So that corresponds to this little triangle that's in this first diagram. Now we can use this result here, that the centre of mass of a hemisphere is 3/8 times the radius of the hemisphere, 3/8 r, from the plane flat surface. So we know the centre of mass is at a distance of 3/8 r from this point here on the flat surface. So that's this distance here is 3/8 r, and r happens to be little r. So I can put this distance here as 3/8 little r. And it's fairly straightforward now. I can use trigonometry to work out this angle. So theta is equal to, now I've got the adjacent here and the opposite, to the tan inverse of the opposite over the adjacent. So that's going to be r over 3/8 r. Now the r's are going to cancel out, so that becomes the tan inverse of 8/3, and that gives us 69.4439 and so on. So we'll give the answer to three significant figures, so 69.4 degrees to 3 SF. Example 16. A non-uniform cylinder has height 20 centimeters and radius 2 centimeters. At any height h centimeters above its base, the density of the cylinder is given by ρ equals 3 times, then in brackets 2 minus h/50 grams per cubic centimeter. The cylinder is freely suspended from point P that lies on the circumference of its top face. Find the angle between the downward vertical and the top face of the cylinder. So I can see that it's non-uniform cylinder, and its density is given by this function here. So let's start with a diagram. So this diagram is representing what's going on here. Here's my cylinder in equilibrium, freely suspended, radius 2, a height of 20 centimeters. Here's its center of mass, which we need to find. Here's just a bigger version of what's going on. So there's the radius. This is a length we need to find, the distance between this face and the center of mass. And once we've got the length of that, we can then use it to work out this angle, which is between the downward vertical and the top face. So that's going to be the top face there, and that green dotted line there represents that line going down to the center of mass. So let's start by calculating the center of mass. Now it talks about the density given as a function given of h, where h is a distance above its base. Now this is going to be its base here. So when we calculate the center of mass, it's going to be the distance from the base. So we'll have to do like a little calculation then to work out what's the distance of the center of mass from the non-base, the top of the cylinder. Now this is the formula here that we would normally use, but because the density is given as a function of h, all our x's we need to turn to h. So it'll be h bar that we find, and these x's will also turn to h as well. We do our working. Now just substituting our values. So the top, the limits are going to be 0 and 20, and then h times by, and then in brackets, well actually let's just write it as 3h, and then 2 minus h over 50, rather than having loads of brackets, dh, and then at the bottom again limits of 0 and 20, and then it's just going to be 3 and then 2 minus h over 50. So let's start by expanding the brackets at the top. So that will be 6h, just 6h minus 3 over 50 h squared, and then the bottom part will just be 6 minus 3 over 50 h. So now we integrate. So we'll have 6h squared divided by 2, so that's 3h squared. And then if we got 3 over 50, we divide that by 2, that will become 3 over, no sorry, we're dividing it by 3, aren't we? Because it's going to become h cubed. So that'll be 1 over 50. If you divide it by 3, h cubed between 0 and 20. And then the bottom is going to be 6h minus, now this one we divide by 2, don't we? So that'd be 3 over 100 h squared, again between 0 and 20. Working these out on our calculators, we'll get 1040 at the top and 108 at the bottom. And that simplifies to 260 over 27. Now remember, what we've got here is this distance from the base. So that distance is 260 over 27. We want this distance here, which is this distance here. So we need to do 20 minus that. So I'll just write down distance from top, or top face, is going to be equal to 20 minus 260 over 27. And that gives me 280 over 27. And we're now ready to finish this off, because I now know the length of this side here, which is 280 over 27. So that angle that I'm trying to find is going to be the tan inverse of the opposite over adjacent, 280 over 27 divided by 2. And that's going to give me 79.08411 and so on. So 3 significant figures, I'll give that as 79.1 degrees. So I'll just get rid of that. 79.1 degrees, and that's 3 significant figures. Okay. Example 17. The diagram shows a uniform solid right circular cone of mass m with radius r and height 3r. P and Q are points at opposite ends of the diameter of the circular plane face, so P and Q there, of the cone. The cone is suspended from a horizontal beam, there's a horizontal beam there, by 2 vertical inelastic strings fastened at P and Q, so inelastic string here and here. Given that the cone is in equilibrium with its axis at an angle of 45 degrees to the horizontal, find the values of the tensions in the strings. Given your answers in terms of M and G. Now, to answer this question, I need to do 2 things. I'm going to resolve vertically, and then I'm going to take moments, probably from point T1, P, or T2, Q, to minimize while working. So the first thing I'm going to do, let's start by resolving vertically, so resolving in this direction, and what we're going to get is this equation T1 plus T2 equals mg. So it's going to be nice and easy to start us off. Then what I'm going to do, I'm just going to draw this diagram a little bit bigger and put on this angle 45 degrees to the horizontal, to the axis of symmetry, which is going to be this dotted line, so that I can see what lengths I need to work out. So I've just drawn this plane face here, PQ, a little bit bigger, and the axis of symmetry here. And next thing we're going to do is to work out this length here. So this is the distance of the center of mass of this cone from its plane face. Now, since the cone has a height of 3r, the center of mass is from its plane face is a quarter of the height of the cone, so a quarter of 3r, so 3/4 r. So we can write down this measurement here as 3/4 r. And then the other thing is that the angle between the its axis and the horizontal is 45 degrees. So there we go, we can put on there, so that is 45 degrees there. Now I'm actually going to take moments about P. You could take moments about Q. So if I'm going to be taking moments about this point, what I need to know are, if I've got mg going down here, I need to know this distance. I'm going to have to calculate that to work out what this clockwise moment is. And then for the tension that's going here, I'm going to have to work out this distance here to get my anti-clockwise moment. So to do that, what I'm going to do is to drop a vertical line down here. Okay, now you can see that this angle is 45, which also means that this angle here is 45, and because this is a right angle here, this angle here is also 45. Now, to find the total length of this line here, if I look at this first part here, So that's this right angle triangle here, hypotenuse of R, and an angle of 45 here and here. So the length of this side is going to be R sine 45 or R cos 45. They're going to be the same. So let's write this as R sine 45. So that's that distance from P to that blue line. And then we also need to work out this distance here because we want the total length of this line up to MG. Now, this line here is the same length as this one, and that's from this right angle triangle here. So this length, hypotenuse 3/4 R, and an adjacent angle 45, and also that's 45 there. So this is 3/4 R cos 45, or 3/4 R sine 45, so either one of those. So I will just put that on here. Let's use 3/4 R sine 45. Sine or cos, doesn't really matter, will both give us the same answer. So starting with this clockwise moment, we have a length of R sine 45 plus 3/4 R sine 45, and both of these could be cos 45, times by mg, and that's going to equal my anti-clockwise moment. So that means working out this length here and then multiplying it by T2. So we're looking at this bigger right angle triangle here, which has a hypotenuse of 2R. Now, since this angle is 45, you look at this right angle triangle, that means that this angle here is also 45, which means the length of this side is 2R cos 45 or 2R sine 45. Doesn't matter which one I use. So let's use the 2R times by sine 45, since we've been using sine, and that we times by T2. So this is now our second equation here, and we can solve it simultaneously with the equation we got when we resolve vertically. Now I've just corrected this part here. I think I wrote 3/R. I was meant to write 3/4 R for that. Right, so let's simplify this and see what we get, this second equation. So that will become 7√2 over 8 RMG equals root 2R T2. Now we can divide both sides by R, we can divide both sides by root 2, so that will leave us with 7/8 mg equals T2. So we've got the value of T2. T2 is 7/8 mg, and we've been asked to give the answers in terms of m and g, so that's fine. So now we can use our first equation to work out the value of T1. Now we know that T1 plus T2 equals mg, so T1 plus T2, which is 7/8 mg, equals mg. So from here we'll get T1 is equal to 1/8 mg, taking away 7/8 mg from both sides. So we've got T1 is 1/8 mg. So we'll just highlight that, and then we'll move on to the next example. Example 18. Two smooth uniform spheres of radius 4 centimeters. So these are two smooth spheres, radius 4 centimeters and mass 5 kg, so their weight is 5g, are suspended from the same point A. So these points here are A, by identical light inextensible strings of length 8 centimeters. So this is length 8 centimeters. Now I've drawn a line going right towards the center, so this is going to be 8 centimeters going towards the center, but the string stops at the surface of the spheres. We know that the spheres hang in equilibrium, touching each other. What is the reaction between them? Now I'll just add this bit of information here that the centre of mass of the spheres is at their centres. That's why I was able to draw the 5G going from the very centre of both of these spheres here. Now to do this question, I'm going to be resolving horizontally and vertically. Now to do that, I do need to know what the horizontal and vertical components of the tension are. So let me just draw a right angle triangle over here, where this side is the tension. Let's call this angle here theta, so that the side at the bottom is going to be t cos theta and this side t sine theta. And maybe with the lengths we can work out what theta is later on in the question. So yeah, let's start by resolving vertically. So by resolving vertically, we have 5G and 5G going downwards, so that's 10G, and that's going to equal by what we've got going up. And let's put some arrows on here like this. So this just represents one of the tensions. They're both going to be the same in slightly different directions. Yeah, so going up, I've got t sine theta from both of those. So I've got two lots of t sine theta, and then I'm going to resolve horizontally. Now when I do this, I'll just consider one sphere, because if I do both together, I'll end up with an equation which will basically just end up being 0 equals 0. So if I look at this sphere, for example, I'll have r, that normal reaction, is going to equal to t cos theta. So r is equal to t cos theta. Now if I take the first equation divided by the second equation, I'll have 10G over r is equal to 2t sine theta over t cos theta. Now I can divide both sides by 2, so I'll get 5G over r is equal to, and that will just become tan theta. Now let's work out what tan theta actually is now, or theta. So we know that the length of this side here is 8. No, it's 12, isn't it? Because it's going to the centre of the circle. So that's going to be 12 for that length there. The bottom is 4. Using Pythagoras, the square root of 12 squared minus 4 squared gives us 8 root 2. So that means that the tan of this angle is going to be 8 root 2 over 4. So we can have 5G over r is equal to 8 root 2 over 4, and just becomes 2 root 2. So from there we can find r. R is going to be 5G divided by 2 root 2. And that leaves us with 5 root 2 over 4G. Now we can leave our answer in terms of G, or we can round that to 3 significant figures. We times that by 9.8, and that gives us 17.3, I think, 17.324. So yeah, if you wanted to give it to 3 significant figures, 17.33 SF, and that's going to be newtons. So you should now be able to do exercise 3D on pages 107 to 109.